Now, I am proud to present the next panel, which is Driving in Education for RISC-V. The panel with me chaired by Maria Rivera, who is the manager of training and education at Barcelona Supercomputing Center, and also a professor at Universitat Politècnica de Catalunya. So whenever you want, Maria, the floor is yours.
So thank you very much, Alberto, for your introduction. Good afternoon to everybody. Thank you very much for attending this panel. It's a pleasure to moderate the panel on driving education in RISC-V. I do not have to motivate the need to join efforts towards properly designing and introducing RISC-V into university curricula, because Mateo Valero has done it strongly. So I can go directly to the introduction of our panelists. And today it's my pleasure to share table with our colleagues that on top of their amazing research, they found time to work on RISC-V and the introduction of RISC-V into university curricula, right? So just in the order they are sitting, it's my pleasure to introduce Katalin Olcoz, who is a professor at Universitat Politècnica de Madrid. Universitat Complutense de Madrid. We are neighbor, yes. Thank you. So my colleague Miquel Morató, professor at Universitat Politècnica de Catalunya and also team leader at Barcelona Supercomputing Center. And Dr. Sarah Harris, professor at University of Nevada, Las Vegas. She authors a book on computer architecture with RISC-V, with an FPGA platform associated, am I wrong? And finally, Dr. Thangxi Tan, who is co-director of RIOS Lab, RIOS stating RISC-V International Open Source Laboratory, and also associate professor at Tsinghua, and had previous experience in curriculum design in Berkeley also. So I think that I give the floor to them. They will present what they have done in their universities, and at the end, they will be ready to answer our questions, to share their thoughts, and to start a nice conversation. Thank you so much. So please, I prepared alphabetical order, so Sarah, you are the first. This is the...
Okay, great. It's great to be here. Thank you for inviting me. Yo creía que tenía que hacerlo en español, pero no, está bien. It's lucky for you, we changed to English because it would probably not go so well for me in Spanish, although I like to try. So I'm from the University of Nevada, Las Vegas. I graduated with my PhD at Stanford almost 20 years ago, which is crazy, with Bill Daly as my advisor. And I worked at Harvey Med College as a professor for 10 years before moving to University of Nevada, Las Vegas. So I wanted to talk about a few of the resources that are available for teaching RISC-V and bringing it into your classes. And so the four main kind of areas are RISC-V International, so the foundation. They have a whole site that lists kind of the current resources. And the nice thing is that's constantly being updated. And if you have resources or you know of resources that should be there, you can submit that request. So that should be pretty kind of current. And then textbooks that are available, online courses, and open source processors. So I'll talk about each of those briefly. So this is the RISC-V International page that lists kind of the 3 areas of resources for education. You can join this special interest group, this RISC-V SIG, and you can also submit content. So if you're interested, there's the link too. So textbooks, I'm featured a little bit more than probably I should be on this page, but so the first is the RISC-V reference, and I think probably many of you have seen that and used that. This is more of a reference manual, and we refer to it as the Mona Lisa book, but I don't know what most people call it, but this is the one by David Patterson and Andrew Waterman. And last time I talked to him at the summit, he said they want to, he's like, that's on my list, is to update that. So maybe there will be a new edition sometime soon, or not. He seemed a little bit skeptical if he would get to that on his list. But, and then the computer organization and design, I think probably many of us have used this, not the RISC-V version, or currently use the RISC-V version in our classes. But this is more a senior level course of architecture. And then also digital design and computer architecture. This is a textbook by myself and my co-author, David, who I'm not related to. We just have the same last name. But we go from very basics, logic design, all the way up through designing a RISC-V processor. And so it's pretty great because in one course, well, at Harvey Mudd we teach it in one course, many places teach it in 2. At University of Nevada we teach it in 2. You can go from learning the basics of logic design to understanding how processors work. So, but in that textbook, we build a kind of toy processor where we don't implement all of the instructions. And so the next book that's, there's no cover page because it doesn't exist yet, is a RISC-V system on chip design course. Am I really loud, or does it just seem loud to me? No, okay. RISC-V system on chip design textbook. And this is a book that my colleagues, David Harris, James Stein, and Rose Thompson are working on right now. And it should be out around in about 1.5 years, so in the beginning of 2025. So this course will bring together both the theory and the application. So I think many of us in graduate school or wherever we learned our whatever we didn't build ourselves, it was kind of theoretical. And so this book actually goes through the entire implementation, including an accompanied open source processor that runs Linux. It runs the entire instruction set, including extensions. So I just wanted to show, this is the table of contents for the textbook. So it goes through the entire kind of process, including design verification, the basic processor with the RV32 and 64 I-based instruction set, and then the extensions as well. So this really not only helps define the theory, but also the practice. How do we actually implement this? So we're really excited about this book, and I wish I had this when I was in graduate school. So this is kind of a senior level, master's, PhD level course, whereas the first book is more for undergraduates. So a bunch of online courses available. Linux Foundation has a lot of them. I just listed a few here. These courses are all listed on that special interest group page from RISC-V International. There's also a YouTube channel. We have a bunch of resources, including an edX course and YouTube videos. Those have been actually a lot more popular than I suspected. We prepared them during the pandemic and just shared them with everybody. So that's kind of useful. One of the courses is called RISC-V FPGA. And this course is developed by one of my colleagues, Danny Chaver, who's at University Complutense de Madrid, and myself, and a bunch of other folks as well, but mostly Danny and myself. And really gets, this is a way for people to get into RISC-V very quickly and using the tools. So within a half an hour, you can be up and running on a RISC-V processor. So, and here's just a list of the labs that are available there. So I mentioned that our processor, the Wally processor called CVW here, a bunch of open source processors kind of, every year kind of exponentially growing. And here are just a few of them. These are from Open Hardware Group, the top ones. And I think, probably, or at least a few of you may use some of them in your, in your research. And so the Wally processor that is the, that we describe in our book is the CVW processor at the bottom there. And we just recently, about 5 months ago, added it to Open Hardware Group. And the nice thing about these cores is most of them have a verification level. And so you can see what they're capable of and what their verification is. Chips Alliance also has an open source core called VEER, and there are other open source cores that I think will be talked about later as well. Thank you. I think that's all I have for the intro. Thank you. Thank you, Mikael.
Okay, hello again. Well, first of all, I would like to thank Maria for this invitation. It's an honor to be in this panel. I truly believe that education is critical for us as a community and also for the future of our people. So thanks for the invite. And I'm very happy to talk about education in RISC-V. Also, I would like to take the opportunity to thank Sarah for her work. This material is fantastic. I mean, I was not aware of the book, but just looking at the index and all the things that you have, I mean, this is for sure something very useful, and I hope to have some time to take a look at it and incorporate it at UPC, because we really need a book that is useful for our undergrads and graduate students. So my idea was to show a little bit, to explain a little bit my journey into RISC-V and education. I got exposed by chance to RISC-V back in 2011 when I started my postdoc at UC Berkeley. Back then, RISC-V was a local research project at UCB, led by Kristi Sanovic and David Patterson, and it was a fantastic project, but was not my purpose of the postdoc to work on that. I believe Jiangxi was back then already, I mean, he has a lot more experience than me in all the Parlab and all the activities that were done there. He can give you more details. But what I want to say is that back then, I mean, this is 12 years back. I mean, this was a local project in a university, very important, but local. And mostly for research, Krista was using RISC-V to teach in his class, but that was RISC-V in education was 1 or 2 classes in Berkeley. Then in 2013, I came back to Barcelona to work in other projects. And since the official ISA of all the projects in Mont Blanc, and as we said before, was ARM, I went back to ARM. And this was, I mean, lots of projects there until the European Processor Initiative started. So this was back in 2018. Also Panos covered it a little bit. And here the goal was to develop domestic technology for HPC. The main design was an ARM-based design because there was this tradition to do ARM designs. But BSc decided to let a first design based on RISC-V. This is a vector accelerator that we have been fabricating several iterations, and it's very interesting. What I'm trying to say is that this was basically our first big research project, but there was no education in this project. The focus was not on education, it was on research, development, growing IPs locally. And it wasn't until we started DRAC, so DRAC is a local project that we did here in Barcelona, that the universities in the Catalan system, I mean, started using RISC-V in research. So the focus of DRAC was to design some cores that we call Lagarto, to design some accelerators for some application domains, for multiple application domains. And we were looking to align our IPs with the EPI project, and also to start promoting RISC-V in the universities of Barcelona. As you can see with the logos at the bottom, well, you cannot see very well, but most of the partners were universities in Barcelona, UAB, UB, Rovira i Virgili, and UPC, and then there was BSc that was helping them to incorporate RISC-V into the curriculums. So when we started in 2019, the reality was that basically RISC-V was only being used at UPC in a couple of master classes, so not much. After this project and a lot of effort of all the universities, we have a completely different scenario. We have RISC-V being used at UAB in all the courses of the degree. It is a pity that ICTS is not here because he's sick, as Mateo said before, because he was the main promoter of this change in all the curricula. So you can imagine changing all the subjects in the computer science degree to incorporate RISC-V, and this is done already at UAB. UB also started adding many courses in the electrical engineering degree and also in the computer science degree around RISC-V. UPC followed a similar trend. So nowadays, UPC we are using RISC-V in the master and also in the computer engineering specialization. Still, we are missing some courses at the beginning of the degree, but it's something we will do in the near future. And finally, URB started this September teaching in RISC-V. So you can see a clear evolution here in Barcelona. And although this is a local picture of what is happening here, I can say that the same trend is happening all over Europe and in Spain. I mean, CATSA is here in Complutense Madrid. They are doing lots of efforts in that. There are many other universities that are incorporating RISC-V. So this is a trend that will continue, and that for sure we will see more and more universities incorporating RISC-V into the different degrees. Then some lessons learned about this experience, this transition. I would say since 2011, that was a single research project in a single university, until now, we can see that there has been a lot of different tools or different in all the levels of the computer science layer around RISC-V. So nowadays we have emulators, we have simulators, we have compilers, libraries, operating systems. So it's very easy, or I mean, getting started with RISC-V is very easy, and in fact, Sarah presented some slides with all the material that is available in open hardware and the RISC-V international web pages. So there is a lot of material. Still, we are missing things. So I mean, for example, there are some tools that are mostly research-based. They are not still a product. They are not 100% reliable when you are using them in teaching. Because when you have a class with hundreds of students, you want that it works perfectly. This is still not there, or not completely there, but it has matured a lot, and I think that very soon, I mean, we will be able to have this environment for education. Then what else I have? Also, something that was interesting is that there are many companies that are offering RISC-V, not RISC-V, they are offering platforms and packets and applications, online courses around RISC-V, and there are even some RISC-V in India that are promoting this. So for sure, this will improve, and we will reach a point where we can really use these things. What else? Okay, then the other thing, students and lecturers. In general, students in the university, they are very happy to have participate, contribute to open source projects. They are very used to doing it in software projects. But having the opportunity to also contribute to hardware projects, open source hardware projects, I think it's really exciting for them. And in general, lecturers and students are really happy to embrace an open hardware movement like RISC-V. Of course, there are some difficulties, especially when you go to large classes in the first years of the degree. I mean, when you have to teach to hundreds of students, I mean, this is sometimes challenging. You have to prepare material for many people. As I was saying, everything has to work perfectly. This is improving, but still a challenge for us. And finally, the other thing that I believe we really need is to have some hardware platforms with high performance that we can use. I mean, there are lots of small microcontroller style designs that can be acquired, and you have very simple cores that you can use. But still, I mean, for some subjects, I mean, for some courses, you need to have higher performance, to have larger systems, to have multiple cores, to have a many core, and this is still not there. In any case, I mean, there are products that have been announced or that they are already in the market that are promising. Like there is the Horse Creek quad-core from Intel, from Sci-Fi, that is fabricated by Intel. I mean, this is a very interesting product, and there is also the 64-core from the Milk-V project. So once we have these systems, I think we will be in a very good position to really use RISC-V in all the courses of the degree and the master of our students. Okay, just some final comments and thoughts to finish. I would say just, I mean, this is, simplifying a lot, but basically what I believe nowadays, we have that RISC-V is the ISA that is being used in most of the research. I mean, when you go to conference, I mean, when you attend presentations, RISC-V is where the innovation is happening and where the research is being done. This is a reality, at least for academic partners like BSc or universities. RISC-V is becoming the de facto ISA in many universities. It's still not finalized because, I mean, there is a lot of material that is working very well with other ISAs, but this trend, as it is happening here, it is happening in many universities. And what I think is going to happen next is that RISC-V will also be the ISA for industry. At least here in Europe, as Spanish was presenting this morning, I mean, there is a huge investment in new companies around RISC-V. There is also a huge investment in the PERTE chip in Spain. So for sure, RISC-V will have a strong market share in the near future. I'm not sure if 90%, as Mateo was saying, in HPC, but in any case, it will be high. And so I think this is very important that now we start preparing our students to be ready for this new industry that will happen soon in all over the world and in Europe in particular. And that's it.
Thank you so much. Okay.
Hello, everybody. First of all, I would like to thank the organizers of this panel because I think it's very timely to talk about RISC-V and education. And then I have to acknowledge that the material that I am going to present is the work of my colleagues from the department, so I'm not really the author. Cacciani Alcoz plus all the people that's doing great job in competency trying to push RISC-V into the courses. So the first slide will be very fast because it has been explained already. There are strategic reasons to change to RISC-V. In the previous panel, we saw many of them. The second reason to change to RISC-V is that it's open source. Mikel also mentioned it. And there's a very active community with these RISC-V international training groups and all people making contributions, and they are easily accessible to anyone. And besides, what we found in the transition is that the modular ISA of RISC-V helps to teach computer architecture concepts in a better way because I will explain later. So before explaining what are we doing at Complutense University, just some context. We teach different degrees from electric engineering to data science and artificial intelligence. There are computer architecture courses at different levels. Those in blue are already being taught using RISC-V. The one in yellow, we are going to change it this year, and the white ones are still being taught using the previous architectures, ARM, MIPS, Intel, or whatever. So in the first level courses, we changed all of them to RISC-V. These courses have the same approach as the book from Sarah, which is really great. So we go from bits to a C program, and students have to understand how they compile that program, how it translates into assembly, is allocated to memory, and it runs in a very simple machine, which now is a simplified version of RISC-V 32, only the integer module. So before changing to RISC-V, the course had two ISAs, ARM for the assembly part and MIPS for the processor design part. Changing to RISC-V make us increase the coherency of the course, but more importantly, it gave us more time to explain the content, because RISC-V it's much simpler to explain than ARM, and I love ARM. But it's easier to explain, and so we don't spend so much time explaining the architecture, and we have more time to explain more computer concepts. For example, we are now including not only the simplified data path, but also an introduction to the pipeline version in the same course, and it was okay for the students because they have only one instruction set and a simpler one. So we developed the labs for the assembly labs just using some IDE for embedded C++ plus a pre-built toolchain for RISC-V, and it was easy to use, and we didn't have any problem with it. So in the second year course is the yellow one. So we decided what to do, but we still didn't do it. And here there are more problems. So this course is a more advanced course. We explain all the modules, CPU, cache memories, virtual memory, I/O, buses, everything. And we have a lab with peripherals, and they have to control the peripherals. This lab is traditionally used single-board computers, such as Raspberry Pi or other boards, depending on the degree. And then we have an expansion board with peripherals. We couldn't buy new boards because we recently bought more than 100. So we are still using the old labs, even if the material for the slides and the explanations in class are planned to be RISC-V oriented. So again, we could get more content into the theory, but here we have a problem with the labs. Then we have an advanced course only for electrical engineering students, and we are very looking forward to Wally. Please, Sarah, hurry up. So the course deals with performance engineering of software for DSP, and it's mostly a practical course. So we just do some performance analysis on soft cores on FPGAs. We previously used MIPS FPGA, and we changed to RISC-V FPGA, which Sarah presented before, and the results were really amazing. Students were much happier with the labs, mainly because the framework in the virtual machine had 0 problems, so they didn't have to spend time dealing with the boards that's not working or anything at all. And then it was easy to use. So it was robust and easy to use. And also RISC-V has very easy access to performance counters that allow us to make new labs and develop more interesting labs, because we had an easy way to access many information inside the core. So it was a great success. So to end up, I will say some of the challenges, even if some already Mikel said. The first challenge is we need to persuade teachers to change their materials, but I think that we are in a good moment because now there are changes that are going to be made all the way. The computer science curricula is being reviewed. The ChatGPT and all these large language models are being discussed. So I think that we are going to change some topics, and if we change, it's a good timing to change to RISC-V, at least is what I think. And then there's a lot of material available. There are books, there are slides. You can go into the training interest group of RISC-V International, and they have plenty of material available for anyone. So I think that teachers are kind of excited about RISC-V, and that this challenge won't be difficult to solve. Then the second challenge, Mikel also mentioned, some tools are still missing. I don't think that it will take many years, but I think that today there are not some boards that would be needed because the ecosystem is evolving so fastly that we don't have the stability that educational boards need. And also there are economical issues. For example, we at university had a bunch of boards for the labs, and I don't think they're going to let us buy new ones in some years. As for the simulators, Mikel also commented, there are basic educational simulators, there are complex research simulators, but there's still some gap between them that needs to be covered. So I think that we are in the way, and in not a long time we can solve these problems, but still we have to do some work about them. And finally, I think, as a final thought, that RISC-V is both a challenge and an opportunity. Our biggest challenge, at least at my university, is to motivate the students, and I think that RISC-V is give us a chance, because students like new things. They love to be taught things that are new, not the, okay, you can teach addressing modes using MIPS, okay. But if you tell them that you are using addressing modes in RISC-V, it's easier to engage them. Then they also like real-world boards, examples, and not just academic toy computers. At Cantabria, you did a really nice work. You published a paper about using Raspberry Pis. It was great. So I think that RISC-V makes it easier for us, because you can use small real-world examples with just the integer part, and then you can use bigger examples with more modules, and they are all real-world, not fancy toys. So I think that this is a second advantage. And the final one is that being open source, RISC-V allows a student to try on their own. and this accessibility will help to motivate them. So that's all from my part.
All right, thank you, Maria. Thank you, everyone. It's my pleasure to share our experience on RISC-V and also RISC-V education. So, wait, sorry, the other way. Okay, here we go. So first, let me give a brief introduction. What is RIOS? RIOS is kind of international open source lab centered around RISC-V. Right, this is a nonprofit lab. So my advisor, Dave Patterson, and I, we set up this lab, almost 3 years ago in Shenzhen. So, and it's actually modeled after, Berkeley Power Lab, right, where, Miguel and I was, doing our PhD work. So this lab is kind of, joint program by Tsinghua University and Berkeley University, probably two best universities in engineering on both, Bay Areas, I think. And also we have lots of industry members, like the Imagination from Europe, and also from like Intel and Analog Device, and also some of the we call like local industry company, for example, ByteDance, right, kind of mother company for TikTok. And also we have very deep collaboration with Google. So it's quite international, and it's nonprofit. And everything we develop is open source and be available to everyone globally. So let me tell you the current education we have. Since RIOS is actually a part of the Tsinghua University, it's actually a grad school. So we don't offer undergrad level courses, but we do have graduate level courses. There are primarily two courses that myself is teaching at this moment. The first one is the advanced computer architecture. This is actually matching Berkeley CS 252. Where we use the RISC-V as the main ISA, and also we do lectures on advanced microarchitectures, for example, auto order and vector architectures. Also, we have 3 labs, 3 really hands-on labs that every student has to go through, and also a final project. But one thing I want to mention that is the lab are all in open EDA. That's actually one of the direction we're very interested at this moment. So we're not using the commercial EDA anymore. We start teaching students to use open EDA and the hacked EDAs. And also, we have another, we call auxiliary course, but it's really kind of the required course, mass teach, mass learn course in computer system. Think about this like light version of UC Berkeley CS 262, which is the really advanced operating system. And what basically do is we teach students read classic papers in operating systems and databases. So basically, we're teaching students about the old ideas, let them try and understand why the architecture decision were made. So we think this is very important. Even we have future technologies must be constrained as like the old one. So not knowing the history or ignoring the history, we're doomed to repeat it. So this we think is very important. Although it's not related to RISC-V, but if you look at lots of fundamental architectures when we design RISC-V ISA, coming from those basics principles from the system courses. And also, I think one of we think it's kind of really we call like innovation, or it's more like an attempt for us is to really trying to combine the open EDA along with the RISC-V in research. We also did a couple of open source tape out along with Google and the Skywater team. So this is a project we call Green Rail. This is also open source. I think it's already second generation. We tape out a couple of times through Skywater 130. And also early this year, one of our students, and I think they actually won the design contest at the ICC. So this is kind of like the first design contest done in open source EDAs, and we did a RISC-V design for that. And also the RISC-V design we done. Consider think about it, it's more like the most complicated design so far the OpenEDA has been seen. So that community kind of right now using this design to drive things forward as well. And also recently, we also have lots of interest on AIs, especially generative AIs, especially this year after ChatGPT has been out. Early this year, my students has been participating in another design contest that I think sponsored by eFabless. This is trying to use generative AI to design open silicons, right? This is, we're one of the participants and we're actually one of the winners. I think the first one is an NYU team. They did a portion of the CPU design, but we use LLM, ChatGPT, and design a full 5-stage pipeline, RV32i. And also, we actually fabricated this chip as part of the the winning designs, and it's 40,000 gates, so it's really reasonable size, and we think there's also lots of opportunity moving forward, just converting the current what we call like chisel-based agile hardware development to AI-based agile hardware development. So this is actually one of the active areas we've been looking at. And these are all the good things, but there's still lots of challenges. But especially, I think, for this community, if you're starting teaching RISC-V, I'm pretty sure you'll meet, one of these, challenges we have. So here's actually one of the surveys we have done in last year about all our incoming graduate students. So we actually promised, the university we're probably going to produce at least 100 CPU designers for the next, 5 years. But still, like roughly among 50 students, graduate students, there are masters and PhDs. We did a survey with them. So one of the problems we found is lots of the students these days are really the lack of background in chip designs, and especially computer architecture and the systems, right? If you look at in the industry, given the past 20 years, they're pretty much very active in internet and AIs, and still today, the AI job market is still very hot. So most of the students, they tend to learn a lot of the software or AI-based courses, but really trying to ignore what the really a CPU designer or chip designer should learn. And also, we think it's very necessary to include very basic VLSI trainings or for incoming students. So I recommend my students to Sarah's book. There are some labs you can follow. That's actually very, very good to start. Most of students this day we found they have very heavy AI and machine learning software trainings background instead. But sometimes, this is not necessarily a bad thing, right? Especially considering, we're looking at how to use AI to design RISC-V, how to use AI to, to change the field. But still, learn a little bit basic, VLSIs is very good to, you gain the domain knowledge, so you can do a much better job in research. I think for most of the students today, almost every new incoming student, they need a retrain. We call it a retrain process. Well, basically what we did was trying to use two very fundamental courses for the students. One is the C1C, that's basic machine structure. We teach RISC-V assembly, very basic 5-stage pipelines. The other one is Berkeley 162. This is operating systems where you learn how the software interact with the hardware, right? So these two basic courses we think every incoming student needs. If you haven't learned it, you have to make sure you learn it by itself. And also, I think there's also from the resource side, I think the schools, and especially even given the Tsinghua or like Berkeley, as I know, we're still lacking of the teaching resource in computer architecture and also VLSIs, right? So this is actually coming from the same survey from our students. When we asked them what is the challenging problem you have, the top issues they have, lots of them they said there are not enough computer architecture or hardware courses in the curriculum, right? So, and also some of them asking we need a lot better introductory courses so that even they want to learn, they have a good course to learn. I think this is kind of really the dilemma we're facing in this industry, given, I mentioned, AI, the internet pretty much dominate the industry. Lots of graduates, very good graduate, very few people like me and Miguel so went back to the academia, right? Still, myself, still spend a lot of time in the industry. So that means even, at the top schools where really lack of the faculties, lack of the, expertise for teaching students. I think this is something, that's why we think we should, as academia, we should collaborate, especially globally, not just, a single country or a single region can do the job. So I think sustainability, at last, I think sustainability in RISC-V training is also very, very important. Assuming you have done a really great job at grad school, like say for master's program, some with thesis, some which is the course, 2 to 3 years, that's usually be the max. But if you let those students go to the industry, 2 to 3 years experience, you still consider very junior. Most of them haven't even fab a chip, haven't even go through the whole chip tape out or bring up process. So that means we need a strong industry behind us just to provide enough like professional trainings, right? Even when they go to industries, you still need the trainings and at the work. You need a workshop, certificate, and so on and so forth. I think RISC-V International has done some spearheading work on that, so that's a very good direction. And also the academia, really needs a strong industry so that we can eventually keep those talents we trained in this field. So it's not very uncommon for our students, train really, really well and then switch to, finance and investment because the industry is so hot. That's very easy to, to get money by investing some other people than building the stuff yourself. Which means in industry, we really need a serious project, and so we keep those talents and further let them to see the career path, further develop the careers. So that's actually very important. So last, I think RISC-V is really global phenomenon. So does education, like I mentioned, where almost everyone is lacking of resources. We really need open and global collaborative communities to work with each other. So that's why I'm here to speaking. Right. Thank you.
Now? Yes. So thank you very much for a nice overview of what is in place. And now it's time for the audience to ask questions. So please, is there any question for the panelists? No? Maybe I would like to ask you, what would be the kind of jobs for which we are training students? What will be the kind of jobs to which RISC-V education makes sense, right? Who can answer?
All right, so I'll probably take this. Technical jobs to train RISC-V. I think number one is not RISC-V itself. We need students get really the solid background, right? So basic VLSI training and also some of the basic OS trainings are very important. So once you get this training, it's very easy for them to feel the beauty of the simplicity in RISC-V, and it's much easier later on. So that's, I would say, make sure they prepare well enough in their circuit background, digital circuit design background, a little bit OS background. Yeah.
Someone else?
So let's see, I think Sonia. The obvious one is processor design, but there are not all that many jobs there. But processor design, it also goes over to GPU design. I've worked for NVIDIA, Hewlett-Packard, designing processors, and just the concepts and the ability to design complex systems carries over to almost any chip design project. And then, I think beyond that, at least in the US, I think we're tending to kind of separate more and more our software and our hardware. And so software, programmers go along a track, and some of them actually aren't even getting computer architecture, kind of high level, maybe like assembly language, but deeper, hardware. We're starting to lose that, and I think that's a really big mistake. Because I think the hardware, software co-design, so being able to understand a processor, and I think again, I think like was said in the earlier panel, RISC-V will be everywhere, right? There were 20 billion processors shipped just last year in 2022. And that's just, the very beginning. So, especially RISC-V, knowing that whether you're a programmer or a hardware designer, I think will be critical, so you can take advantage of the hardware resources. So I think it's useful across the board for hardware and software design.
Well, I fully agree. I mean, especially for software developers, being able to understand the hardware, the architecture that is below that, and how to run applications efficiently, this is very important. And I think with RISC-V we can simplify all the description of the hardware, the microarchitecture, see all the different levels in the computer system stack, and then being able to program efficient applications.
Okay. More questions? Please.
So on the topic of training for industry, my question is why is it that university focus so much on either the use of the computer with software or the very, very, very low level part, the processor design, for which there aren't really very many jobs? When in reality, most of the jobs for hardware people are in the in-between space. That is, how do you use processor IP to do something, to make something that software can use, right? This is where the co-design is happening. So how can you do more training in that space?
Do you have an answer?
I don't know if I got the question right. If not, please tell me. I think that part of the problem is that there is a gap between people that teach computer architecture and people from the applications and middleware world. And I think that we have to talk between each other, because the way that computer architecture needs to be explained, we may have to change some things, because we have to explain what are the implications in the higher levels of the different choices that the computer architecture has to do. In that sense, the book that we are using, the book from Sarah, it's very interesting because it goes from a C code and explains all the process that code has to be transformed, and then how it is executed. So I think that that's one step in the good direction, but I think that we have to rethink the way we are teaching students. In most computer science schools, they don't know about parallel programming or memory coherence or many other things that are really important for high-performance programmers. And I think that there's a problem of not collaborating between different areas of research and of teaching. I don't know if that answers your question.
Yeah, so I agree with Katja. That was kind of my point, is that I think we're actually, in some cases, moving in the wrong direction, where, at least in the US, where we're separating even more the hardware and software. And I guess that, another to that point is, agree with Katja, we can do better by showing how you actually apply what you learn in the hardware classes to your software. And so I think we can bridge that gap, and we don't. I agree with you as well that we need to bridge that gap a lot better. I mean, you can see it just in the performance, and that very few programs use more than one core, even though there are 4 or 8 available. So that's a big, that hardware software co-design. I think that was my my point earlier is, I think we need to strengthen that instead of moving away and separating them more. So yeah, great point. Anybody else?
All right, so Peter, that's a great question. So in my opinion, this problem, for grad school, we do have solutions, right? You can let the graduate student work on, software, hardware projects. You build the machines and you program the software yourself. But the real problem, I think, is the undergrad training, right? So how can you get the students, really motivate them to work on the hardware? So it's very easy to let students work on the software and the AI stuff, right? That's what I'm seeing. All my students, they have very good, AI background. They know machine learnings. They can do collaborative filtering very quickly, but they know very little about VLSI designs, or some of them even just get digital trainings, right? They don't even know how transistor works, right? But how could we motivate the undergrad student when they first got approached this field, right? So they really see what's really going on underneath, or under the hood. I think that's actually very, very challenging.
Well, so I do want to say to you that that is actually one of the main motivators for us writing our it's our 3rd book, but the first RISC-V book was to demystify that process from transistors. We start with logic gates, go all the way down to transistors, all the way up to programs running on a processor. And I think that, I know for me, I kind of had to piece it together between courses, but it kind of opens your mind to how it works. So I think that that whole train is important. And as far as there are not that many processor, GPU, CPU. I mean, there are a lot, but relatively fewer jobs. But the wonderful thing I think about having RISC-V processor as a platform is it's a very complex system, right? And so the principles that you learn there apply to other complex systems that you may design. So maybe you won't be working with a processor necessarily. Maybe you're building some kind of accelerator. The principles that you learned apply across the board, but I think we can do a better job of showing how those principles apply. So, thank you.
Okay. More questions? Were there? I think it would be the last, isn't it, Alberto? Yes?
I'm very lucky. I always make the same last question. You are speaking a lot about software co-design. But what do you really mean by software co-design? That is, what I think of is that you're thinking at a matrix vector multiplication or a matrix-matrix multiplication. But to what extent one can propose something different, like a graph algorithm, or so what I miss a bit is what is the mechanism to really make this co-design. On my side, I should say I have not a clue about hardware, okay?
So I'll start really quickly. So I had a project with Intel and 5 students, 5 undergraduates, and one of them was to basically take an algorithm and make it faster just by the way you program it, right? And so I think I can't remember the end numbers exactly, but something like 50x if we use, all of the mechanisms that are available, like prefetching and different. So the hardware software co-design is really showing how can you use the hardware effectively.
This is telling to the software user that he needs to use the hardware. It's not co-design. It's not making any effort to change the hardware so that the given algorithm can.
So you're saying it doesn't go the other way. So you're saying
so
the software. Well, that it's kind of Ondel's law of, well, let's fix the biggest gap first. And I think that's the biggest gap is, right, like the hardware is underutilized. And so I think I agree that there could be feedback the other way. And I think there often is, right? That's why we have accelerators. That's how accelerators happen. Yeah. Is because in software it says, hey, you know what, this is really slow. get us a GPU. Okay, so that's how that actually started, right?
Yes.
So there definitely is the other direction as well.
So what I'm trying to tell is, for example, it is very, very established to use the LIMPAC as a benchmark. And who did the LIMPAC or the BLAS really knew how to use any mechanism to go down to squeeze the last performance. But there exist other benchmarks, the HPCG, the graph, I don't remember the name of the suite, but there are graph suites. They should also be objective of optimization, not just the dense algorithms, because they are the ones that are fashionable now for AI.
So I agree with Sarah. I mean, there are plenty of opportunities to do this co-design both at software and hardware side. I mean, if you look at the latest products from NVIDIA, all vendors, AMD was presenting also, they have accelerators for AI. I mean, this is something that without the software that really needs the extra performance, I mean, they wouldn't be there. And you have these tensor processing units. I mean, this is for dense multiplication operations. I mean, this is very typical. I mean, this is very old, but there are accelerators that are now incorporated into products and are very useful. Also, Intel or IBM, ARM, they have now these matrix extensions. So the ISA now has support to do operations with small matrices. This is something that didn't exist before. And these are all the vendors. I mean, if you go to startups, there is a plethora of AI startups that are doing custom hardware here in Europe, in the US, China. I mean, so I really think that this hardware software co-design, there are plenty of opportunities, and RISC-V precisely opens the door to do further hardware software co-design.
Okay, thank you so much. I think that we can conclude that RISC-V will be a key actor during the next 5 years in education, right? So thank you very much. Please join me in a big thanks to the panelists, no, for their contribution. Thank you very much. So, and I pass the floor to Alberto to provide the last indications. Thank you so much.